Alright, welcome back to another episode of Math with Haas. We're watching Precalculus Season 1, Episode 13. Now, we are continuing our examination of applications of exponentials and logarithms, and in this video we're going to talk about Newton's law of cooling. So, what Newton's law of cooling models is, if you imagine you have a cup of coffee or tea or something, and you leave it on a counter, we all know that its temperature will go down. So the question is, how do we mathematically model that? Or if you have a soda, you put it in the refrigerator, you wonder how long will it take for that soda to cool down? Well, we can model this using Newton's law of cooling. So what the Newton's law of cooling says is the following. We have our temperature of our object. Let's start over on that. We have our, so there we go, that looks a lot better. We have our temperature, capital T, and that's going to equal T subscript S. So T subscript S is the surrounding temperature. So this means things like the room. So if you have a cup of coffee out in the room, TS will be room temperature, surrounding environment temp. If you place your beverage in a refrigerator, then the surrounding environment temperature will be whatever the temperature of the refrigerator is. Likewise, if it's a freezer. Alright, and then we're going to add to this a T naught, where you could probably imagine by now that T naught is again the, we can say, let's say the initial temperature. Yeah. So what we want to do is say initial. So we are going to say this is the initial temperature, but we want to say it's the initial temperature difference between the object and its surroundings. Alright, so if you have like a cup of coffee that's at, say, 100 degrees temperature, and then if you are in a room of 70 degrees, then T naught would be 30. Okay, 100 minus 30. And then since we do have temperature decreasing, we can expect a negative here, and then we're going to have a KT. So lowercase t is just time like normal, but K, it is not going to be a rate like our R, even though it's functioning in the same way. What K is it's going to be a constant dependent upon the type of material we're dealing with. So this is dependent on the type of material. So K will change depending whether you have a turkey that's cooling down fresh out of the oven, or if it's like a cup of coffee cooling down, and then like a can of soda, that will have a different K value as well. So keep in mind K is determined by what kind of material. Okay. The derivation for this equation requires a little bit of calculus, so we'll save that as something for a future video when we get to the appropriate material. So let's go ahead and work through an example. So suppose you have a cup of coffee at a temperature of about 200, let's just say 200 degrees. Fahrenheit, and is placed on a counter in a room at a temperature of about 71 degrees Fahrenheit. And then we observe that after let's say after 5 minutes, the that's not how you spell temperature. The temperature of the coffee was about 180 degrees Fahrenheit. Alright. So far we have a nice little paragraph. Suppose you have a cup of coffee at a temperature of 200 degrees Fahrenheit and is placed on a counter in a room at a temperature of 71 degrees Fahrenheit. After 5 minutes, the temperature of the coffee was 180 degrees. So now let's come up with some questions. One, let's say, make a model. Make a model for this cup of coffee. 2, find the temperature of the coffee after about 20 minutes. 3, how long will it take for the coffee to cool down to, how about let's say room temperature. Let's see what 71 is to 71 degrees. How long will it take for it to reach the temperature of the room? And then, yeah, we'll call that good. Alright, so we got 3 questions here. So let's start with looking at what is given to us. So we have a temperature of 200 degrees. We're told that's a cup of coffee. Okay. And we're told it's placed on counter. So room temperature's 71. So this tells us that TS is going to equal 71. Okay. Now, this 200 here is related to T naught, but it's not equal to T naught. Remember we said T naught is equal temperature of object minus the surrounding temperature. So that means that T naught is going to equal 200 minus 71, which is equal to 129. Alright. So then, now we're not told what K is, because we read here, after 5 minutes, the temperature of the coffee was 180 degrees. What this is a coordinate pair. So this is a T value, and this is a capital T. So think of this as a coordinate pair where it's equal to 5, 180, or if you want to think of it this way, T is equal to 5, capital T is equal to 180. We can use this information read, however, to set up an equation to find K. So we know that 180 is going to equal our surrounding temperature, 71, plus our T naught, e to the negative k times 5. And now we can solve this system of, or this exponential equation to find k. So this is all work so far for number 1. So subtract 71, subtract 71. 109 is equal to 129 e to negative k times 5. Alright, so then we need to divide by 129. By 129. Then we have 109 over 129 is equal to e to negative k times 5. Now we need to take the log of both sides. We'll use natural log. So natural log of 109 over 129 will equal the natural log of e to negative k times 5. So just to review what we're doing here, we start out for our exponential equation. We are isolating the exponential, so we have e to negative k times 5 isolated. Now that we have it isolated, our next step was to take the log. In this case, we picked natural log because we have our property where natural log of e to the x is equal to x. And so we can think of this natural log and exponential killing each other off. And that's just by our properties. So we are left with natural log of 109 minus natural log of 129 is equal to negative k times 5. And we'll divide that negative 5 out. So k will equal natural log of 109 over 129 over negative 5. Alright, now you're probably wondering, well, k here is negative, and if k is negative, then for our equation here, that means we'll have e to a positive, which means it would seem like then our temperature would be growing. So how could temperature be increasing when this equation is supposed to be causing temperature decreases? And the answer to that is the fact that the numerator here, natural log of 109 minus, or natural log of 109 over 129, that's actually a negative number. So really it's a negative number divided by a negative number, making k positive. So let's figure out what k equals. So we have natural log 109 divided by 129 divided by negative 5, and there's our positive k value. I'm going to store this in, how about alpha k? Here we go. So now I have my k value stored in memory slot k. So we can now formulate our equation for number 1. So our temperature will equal, let's see, we said surrounding temperature was 71, our T naught 129, E, I'm just going to write K instead of writing this entire expression right here. So KT, where it's understood that K is going to equal natural log of 109 over 129 over negative 5. Alright, so that is our K value. I'm just not going to write it in our equation or work. So that's one way of writing our answer. You could put that entire number in there for our K. So we could put that whole natural log expression there, but I decided not to write it. Just as long as we make a note off to the side what K is. So let's scroll up and see what number 2 asked. Find the temperature of the coffee after 20 minutes. Okay, so for number 2, we are asked find the temperature of the coffee, so we want to know what T is. And then we know that little t is going to be 20. Little t here is 20. Okay. So we're told, oops, let's undo that. We need to be writing again. So t is equal to 20. So now we can just set this up. T is going to equal 71 plus 129 e to the negative 20k. So 71 plus 129 e to the negative 20k. That gives us 136 degrees. So after 20 minutes, T will equal 136. We'll just round to one decimal place, degrees Fahrenheit. Alright. Now, our last question. How long will it take for the coffee to cool down to room temperature? Okay. We should probably box that. So question is, if t is equal to 71, now that I think about it, that's a bad question. Let's make it 72. And then we'll explain why that's a bad question. Okay? So suppose t is 72. So if t is equal to 72, then we'll ask what does t equal? Alright, so let's set this up. So we have 70, oops, I changed this to 72. So 72 is equal to 71 plus 129 e to negative 20k. So let's subtract the 20 or the 71 over. We have to solve for, why did I do the 20? No, that's bad. That should just be kt, but we already know what k is. So 1 will equal 129 e to the negative kt. Now we need to take the log. Natural log 1 is equal to, oh, no, bad. Oops. Before we take natural log, we need to divide by 129. Divide by 129. So then we can have natural log of, no. Alright, getting ahead of myself here. So we have 1 over 129 is equal to e to negative kt. And now we'll take the natural log of both sides. So natural log of 1 over 129 is equal to natural log of e to the negative kt. And we can cross out that exponential with that log. So natural log of 1 over 129 is equal to negative kt. I can simplify the right side or the left side here as negative natural log of 129. And that's because of our law of logs. Natural log of 1 over 129 is equal to natural log of 1 minus natural log of 129. Natural log of 1 is 0. So that gives us natural log of 129 to negative that. So t will equal natural log of 129 over k. So let's see here, natural log 129 divided by k. So we get t here equaling 144. Interesting. So t here is going to equal 144.2 minutes. So it took 20 minutes to cool down to 136 degrees, almost 137 degrees. It will take 144 minutes to cool down to 72 degrees. So that's interesting. The question is going to be, why is that? And that is related to the question of why it would have been a bad question to pick t equals 71. So if we had t equals 71, we would have 71 is equal to 71 plus 129 e to negative kt. So we would subtract 71, and then that will give us 0 is equal to 129 e to negative kt. Now if you did not realize that it is impossible for an exponential to equal 0, we would divide by 129, divide by 129, get 0 is equal to e to negative kt, and then you have tried taking natural log of 0, and you cannot do that because exponentials can never equal 0, and that means that 0 is outside the domain of natural log, which is why your calculator yells at you whenever you do that. See? So that's why I changed it to 72. Now the other thing we need to keep in mind is, why does it take 2 hours? 144 minutes, right? 144 divided by 60, 2.4 hours. Alright, so why would it take 2.4 hours for a cup of coffee to be almost, I repeat, almost room temperature? So let's go ahead and look at the graph and make an interesting observation. So we are going to Desmos.com. It's one of my favorite websites. So we had temperature was equal to 71 plus 129 e to the negative, let's see here, let's remember what k was. Where is our k? Right there. Negative, let's say natural log of 109 divided by 129 times x. Alright. So in this case, I'm using y for our capital T, I'm using x for our little t. So we got everything plugged in. Now where is our graph? There's our graph. Alright. So there's our, why is yours backwards now? Oh, I forgot to divide by negative 5. Divide by negative 5. That'll fix our graph. I forgot the negative 5 right here. That's funny. Alright. So now let's make our graph bigger. Let's go ahead and turn on projector mode so we'll see it a little better. Alright. So if I were to graph y equals 71, we can, let's turn out for a moment. So we can look here, and as time goes on, this thing, our curve flattens out. In fact, this has a horizontal asymptote at y equals 71. Why we have this asymptote here, we can refer to our episode on graph transformations for exponentials. We talked about how if you have a number plus your exponential, then this value here would become a asymptote, horizontal asymptote. So because 71 is a horizontal asymptote, the temperature theoretically could never reach 71 according to this math equation. So if supposing that this math equation is entirely valid without any other influences, variables, etc., then in theory it would be impossible for our cup of coffee to reach 71. It would, or 71 degrees. It would just get infinitely closer. So as we zoom in, we can see, oh, it almost touches, but it doesn't. And go over here, looks like it touches, but if you actually zoom in, nope, it just gets really close. So this asymptote here is the graphical representation for why when we start solving this for t equals 71 here, why that we got 0 and then we couldn't take natural log of 0 is because of this whole asymptote business graphically. So that's why we picked 72, because that's almost room temperature. At that point, it's good enough estimate for how long to be room temperature. So with that, we'll call it a day for Newton's law of cooling. It's very interesting. There's a couple of classic types of problems on the Google Forms. One concerns Turkey, another one concerns a murder mystery. So I recommend you checking out those problems. If you've enjoyed our content, please subscribe, consider supporting us on Patreon. Thank you for joining our math party, and I will see you next time.